Take three frontier mixture of experts models, operating at roughly 3.6 to 4.0 billion active parameters. Fine-tune these models to reason in a low-resource language, in this case, Greek. Tracking mean accuracy across a 1,000-item probe, the line stays flat at 72.9% for base and fine-tunes, but changing only the random training seed splits the score into three distinct results. That 7.7-point shift is larger than any actual data effect measured. When the noise floor is this high, a single accuracy number is effectively unfalsifiable until a second and third seed are tested. If accuracy benchmarks are this noisy, how do we actually measure what a training run accomplished? The researchers propose an alternative instrument, replacing that single accuracy bar with a 6-axis radar chart, mapping specific behavioral dimensions. These dimensions are specifically designed to exclude metrics that correlate with output length. This prevents the evaluation from accidentally rewarding a model just for being more verbose. Accuracy numbers tell us if the final answer is right, but these behavioral probes reveal the shift in how the model reaches that answer. Without them, we miss the internal changes that a flat benchmark cannot see. Before tuning, the models fail the core requirement. They never think in Greek, even when the question is asked in Greek. Out of 1,000 reasoning traces, exactly 0 clear the threshold for Greek character usage. Supervised fine-tuning changes this. After SFT, nearly every checkpoint shifts its internal reasoning to the language of the question. The models now produce reasoning traces in Greek on 97.4% to 98.1% of all items. Compare that to the accuracy score, which barely moved. The results are still getting the same percentage of questions right, but it's doing so with an entirely different reasoning process. SFT installs these complex reasoning habits beneath the surface. It proves a model's internal behavior can transform, even when its external benchmark score remains static. However, SFT introduces defects. It degrades format compliance, often causing the model to ignore the requested structure of the final answer. This leads to answer channel leak, where the Greek characters from the model's internal thought process spill over into the final data output. Reinforcement learning with verifiable rewards is used to clean this up. It separates the Greek reasoning into a hidden trace section, leaving the final answer line clean. The results are mechanical. Answer format fallback, where the model misses the answer line entirely, drops from 24% to 2.5%. Answer channel leakage is eliminated, falling from 3.5% to 0%. Override obedience, the ability to ignore the Greek habit when told otherwise, improves by 9.1 percentage points. Critically, the core Greek reasoning habit survives this RL cleanup. It maintains 98.2% fidelity even after the model is trained to be more compliant. This defines the pipeline. SFT builds the underlying reasoning habit, and RL is required to align that habit into a parsable format. To prove why these new probes are necessary, the authors highlight 5 instances where their own standard instruments lied to them. One unanchored score produced a phantom plus 29.8-point capability gain. That advantage disappeared the moment the scoring was restricted to the requested answer line. They found a logic test set where nearly 40% of the items shared long 13-gram sequences with the training data. Models also scored better on machine-translated math, simply because the evaluation translator came from the same model family as the training data. Even a basic numeral parser failed, mangling comma-separated thousands and turning the number 114,200 into 114.2. This suggests that many reports of catastrophic forgetting after SFT are actually just format compliance errors in the scoring script. Fix the format, and the supposedly lost capability often returns. To stay ahead of research that breaks down the mechanics of these models, subscribe to the channel. When evaluating a fine-tune, anomalies are more likely to be a sign of a broken testing harness than actual damage to the model's weights. Beyond evaluation, fine-tuning MOE models creates unpredictable token economics. This table shows how the same recipe affects different models. Qwen spends 3 times fewer tokens than its base, while GPT-OSS becomes 60% more expensive to run. That cost increase happens because the tokenizer's specific penalty for Greek text outweighs any efficiency gained by the model's reasoning. Steerability is also a surprise. Once a model is trained to a specific language, it resists commands to change. When told to think in English, Qwen obeys less than half the time, and Nematron fails to switch entirely. These serving costs and steerability constraints cannot be predicted from a model card. They must be empirically tested for each specific checkpoint. The researchers include a significant caveat. Their headline 7.7-point variance claim is itself based on a small sample size. Because they only tested 3 random seeds, the confidence interval for that variance is staggeringly wide, ranging from 2.3 points to 27.7. To prove this variance at a 90% power level, they estimate they would need between 11 and 40 random seeds per test arm. These results are also limited to a single language and a single architecture family, mixture of experts trained with LoRa. If this 7.7-point swing survives in dense models with full fine-tuning, then any paper reporting a single-run gain of 6 points or less is essentially measuring noise. But if it collapses, we're looking at a specific instability in MOE routers. Either way, a single seed is no longer enough to validate a fine-tune.